So your empirical formula. So we're going to talk about empirical formulas first, and then molecular formulas afterwards. So first thing is the empirical formula, which is what we've been using. This is obtained from experimental data, and it's the smallest whole number ratio of atoms in a compound. So for example, CH2, C2H4, C3H6, etc. They've all got a simple ratio of 1 carbon to 2 hydrogens. So the empirical formula for all of those is just CH2. So we're just simplifying it to the lowest common terms, and that gives us the empirical formula, just the lowest whole number ratio, CH2. So we know that for compounds, long before we understood about combining capacities ion charges, that they were determined by lab analysis. So before we actually understood anything about how different things combined, we knew their formulas by analyzing them in labs. So the amount of each element in the compound was measured, and then the simplest ratio of those atoms in the compound was determined. So for example, CO2, using the ratio in that, which is 1 to 2, we can say that in 1 molecule of CO2, we've got 1 atom of C, carbon, for every 2 atoms rather, of O, oxygen. And then we can say in 2 molecules of CO2, we have 2 atoms of carbon to every 4 atoms of oxygen. So we're just going up with this 1 to 2 ratio. In 1,000 molecules of CO2, and we're just shorting molecules, so molecule, we're going to have 1,000 atoms of carbon to, yes. Oh, did I not have enough far enough? Okay. To 2,000 atoms of oxygen. Here's a gigantic number. This should be a little 23 up there. Sorry about that. In 1 mole, so where we've got 6.02 or 6.022 times 10 to the 23, we've got that number of atoms to 2 moles. I'm just going to do that. And then obviously you could multiply that out and you get like 12.04. Okay. 1 mole of CO2, we could write 1 mole carbon atoms to 2 moles of oxygen atoms. And then in 44 grams of carbon dioxide, using our molar mass, we would have 12 grams of carbon if we've got 2 oxygens, which are 16 grams per mole, we would have 32 grams of oxygen. So that's for molar mass. So, give you guys a second for that. So that's just using that ratio. It's going to always hold true in all those different scenarios. So what we're going to do is we work backwards from knowing the mass of each of the elements in a compound. So we know the mass of oxygen, we know the mass of carbon, for example. So what we can do is work backwards to the number of moles of each element. And then we can actually figure out how many atoms of each element are in the formula for the compound. So this knowledge allows us to obtain the empirical formula. So working backwards, using that mass, we can figure out what the empirical formula, so the lowest possible terms, is. So an example is if a compound contains 43.2 grams of carbon and 115.8 grams of oxygen, what we can do is use the mass to determine the moles of each atom, and we can get our empirical formula. So we want to know how many moles of carbon, and we want to know how many moles of oxygen. So we're going to start off with our mass, 43.2 grams of carbon. And then we're going to use the molar mass of carbon, which is 12 grams per every 1 mole. And what we end up with is we have got 3.60 moles of carbon. And then if we're looking at oxygen, we're going to go, okay, I've got 115.8 grams, and I'm multiplying it by the molar mass of oxygen, which is 16 grams for every 1 mole of oxygen. And I end up with 7.24 moles of oxygen. All right, so this is our first step. We're just determining how many moles of carbon, how many moles of oxygen do I have in that sample. And we have to make sure that we're using the right number of sig figs and the unitary rate as a conversion factor. Okay, let's go to the next page here. All right, step 2. So what we're going to do, I'm just going to write down the thing from the last page just so that we've got this. So again, we had from step 1, 3.60 moles C and 7.24 moles of oxygen. Okay, just so we still have that information there. So now what we're going to do is we are going to find the smallest ratio of the moles. By dividing both by the smaller number. All right, so smaller number in this case is 3.60, right? So what we're going to do is, so we're going to go carbon moles will be 3.60 divided by 3.60. So that's just going to be 1. And then oxygen moles is going to be my moles of oxygen, which is 7.24, divided by my moles of carbon, which is 3.60 moles. And what I'm going to end up with there is 2.01. So this is close to 2. We're going to round to the whole number. Can you have 0.01 of a molecule? No. Yeah, no. Not unless you are doing like nuclear fission, which we're not. So we can round that to 2. So what this gives us is a ratio of 2 carbons to every 1, oh, whoops, sorry, my bad, wrong. 1 carbon to every 2 oxygens. So therefore, the empirical formula, so that's an I, empirical formula is going to be C1O2 because there's 2 of them. So that's how we're getting our empirical, our lowest terms formula. Okay, so we're going to do another example. In this case, rather than being given the mass, we're given the percentage. So 70% iron and 30% oxygen is found to be in whatever this compound is. So in order to calculate the moles here, we do need the masses of each element. So therefore, we're going to assume this isn't really important what you assume here, as long as you're consistent with it. But we'll just assume that we've got 100 grams. This is a really easy number to work with. So 100 grams is a nice, easy number to work with. We're going to assume that we've got that much of the compound. So it's made up of 70 grams of Fe. And I guess this actually has another sig fig, 70.0 grams of Fe and 30.0 grams of oxygen. All right, so that's what my molecule is made up of, is 70.0, that looks so messy, 70.0 grams of iron and 30.0 grams of oxygen. This is only when you're doing percentages that you would do this, assuming the total mass. You would not do this if you were given mass. So with percentages, we're going to assume we've got 100 grams and just use those percentages as if they're masses. All right, then we're going to use the mass to determine the moles. Of each atom. And then this is the same process as the last one. So number of moles of iron. So we've got 70.0 grams of iron. And our molar mass of iron is 55.8 grams for every 1 mole. So then what we're going to end up with, we've canceled out our grams, and we're left with moles. We have got 1.25 moles of iron. Okay, are we all with me for how we got from percentage to moles of iron? Okay, good. All right, next one, we're going to do oxygen. So how many moles of oxygen are there? I put question marks on both sides of this. We should be like Spanish. Okay, so I want you guys to take a second and figure out how many moles of oxygen there are with a person at your table. Give you a moment to do that. Okay, another couple seconds to get that. Amber, would you just mind opening the door? Yeah. Oh, that's one of your people waiting for you. Okay. So take another second there. Okay, does anybody have a number? Oh, you already did the next step. Nice. Okay, did everybody get 1.88 moles of oxygen? Okay, good. Okay, and then you went into step 2, ahead of the game. So then we're, again, finding the smallest ratio of the moles by dividing both by the smallest number. So I'm just going to write this as if we're setting up a ratio. So moles of Fe to moles of O. And I'm going to end up with 1.25 divided by 1.25 because this is how many moles of iron I have, and my smallest number also happens to be my iron. Okay, 1.88 moles of oxygen divided by my 1.25 moles, which is my smallest number. So here, okay, this one's a little bit trickier. 1 to 1.5 is what I'm going to get. All right. So 1.5 is a much bigger number than that 2.01 we had up at the top, right? 1.5, that's almost 2, right? So instead of I'm not going to round this, what we're actually going to do is find a number that we can multiply both sides by and end up with a whole number. What number can you multiply 1 and 1.55 to end up with 2 whole numbers? Yeah, 2. All right, so we're going to multiply these by 2, and we're going to end up with a 2 to 3 ratio. Okay, so we've got a 2 to 3 ratio. So then what these need to be whole numbers. So the empirical formula is Fe2O3. So basically, as soon as you've got a decimal at the first place here, you should be multiplying to a whole number. Okay. Can I go to the next page? Okay. So we're going to do another example here. We are going to find the empirical formula of a compound that's 81.8% carbon, 18.2% hydrogen. So I'm going to, again, how many grams should I assume I have? Yep, assume you have 100 grams. That will just make your life nice and easy because percentages are out of 100, right? Okay, you do need to state this. If you're being asked a question, you do need to state that you're assuming that information. All right, so I want you all to try this on your own. So give this one a go. All the way down to the bottom here. So you should end up with a ratio and empirical formula. So what I want you to get to is the empirical formula. Yeah, for sure. Or do you guys want to do this one step at a time? Okay, so do step 1, then we'll make sure that you're right, and then we'll do step 2. So do step 1. Does everybody have a number of moles for step 1? I'll give you another minute. Okay, so for step 1, did we get 6.82 moles of carbon and 18.2 moles of hydrogen? Good, okay. Let's find the smallest ratio. What am I dividing by? 12? Oh. Awesome, yeah. So moles of carbon to moles of hydrogen, I'm going 6.82 divided by 6.82. And I'm going 18.2 divided by 6.82. Okay, here is a bit of a tricky. I'm going to end up with a 1 to 2.67 ratio. Whoa, what do we do with that? All right, so this is where your math skills, this should be 2.67. Your math skills are going to be needed here. So 0.67, we need to get rid of that 0.67. What fraction is 0.67, like approximately? Like 2/3-ish? So it's about 2/3. So we're going to multiply this by 3 to clear the fraction. And get a whole number. So if we multiply these by 3, we get 3 and 8.01. That's okay. That is close enough to 8 that we can call it 8. And if you multiply it by a different number and you get something that's not small enough to be close enough to a whole number, that's okay. Just try something else. So therefore, our empirical formula is, what's the empirical formula? Yeah, exactly. 3 to 8, awesome. So that's our empirical formula. Crushed it. Okay, so mathematically, we are getting rid of the denominator. But you don't need to show this process, but the theory behind how this works is like, so this is from here. So the theory behind how we did that is 2.67 is about 2 2/3. No. Yep, 2 2/3, which is 678 over 3. So then when we multiply a fraction by its denominator, the numerator is what's left. So when we do that with a decimal in chemistry, we call it clearing the fraction. We just don't like decimals in chemistry when we're doing empirical formulas. We're wanting to work with whole numbers. You can't have 0.5 or 0.67 of an atom. So we need to clear the fraction. There is a chart. Look at the chart on page.
Pick up in the office for Chelsea Potter. Pick up for Chelsea Potter, sorry. And if anybody lost a Visa debit card, they can claim it at the office. Thank you.
Okay, there's a chart on page 93. This is the last little bit, and then I'll let you go. So you need to be able to recognize the following fractions and decimal equivalents, which are on that chart. And then to clear fractions, you multiply the decimal by the denominator. Okay. So what I want you all to do over the weekend is look at this chart that's on page 93. Try this question. So page 46, A, B, C, D, G, L, J, M. And that worksheet that I handed out alongside these notes. So you guys are doing these textbook questions and that worksheet. We will go over some of them on Monday together. And Monday's a late start day. So don't come to school at 9 on Monday.
All WSS Math Week. Don't forget, you're having your team yearbook photo today outside the portable at 11:45 a.m.